In this video, I'll be discussing the law of reflection and Snell's law of refraction. For this video, I will be using the free physics simulation program that is provided by the University of Colorado, Boulder. So looking at our setup, here's what we have. We have a red laser beam, and this red laser beam is in medium number 1 because this is where the source of light is. Then there's a second medium number 2, because that's where the light will eventually enter. Also, we have our dashed line here called the normal line because it's perpendicular to the medium surface. The normal line is always used when measuring the angle of a light ray. And finally, we have these two boxes here which allow us to control the index of refraction of each medium. But before I discuss the meaning of the index of refraction, I quickly want to discuss the law of reflection. It is a very simple law, and here it is being demonstrated. It simply says that when a light ray comes in and interacts with a surface, if it is reflected, the reflected beam will also have the same angle as the angle of the incident beam. But how do we measure that angle? We always measure it with respect to the normal line. And it doesn't matter if the surface is flat, curved, or irregular. When you get to the surface, you draw a normal line, and when you make your angle measurements, you will always discover that the law of reflection holds. So let's now return to the index of refraction. What does the index actually measure? The answer is, it is simply a ratio of the speed of light in a vacuum divided by the speed of light in the medium. Now, when light travels through a medium, its speed will always be lower than the speed of light in a vacuum. Consequently, this ratio, called the index of refraction, will always be 1 or greater than 1. In addition, it has no units because it is a ratio. Now let's try to answer this question. Why does light change its speed when it enters different mediums? Well, I have this picture here that I'm going to use to try to explain why this occurs. The red line that you see here represents a light wavefront. In other words, it's like a bunch of light particles. Now, let me explain this about light. Light is a subcategory of a much larger category that we call the electromagnetic spectrum. In the electromagnetic spectrum, you have other things like radio waves, microwaves, X-rays, as shown in this chart. But they all have one thing in common. They are all transmitted through space and mediums by photons. So what is a photon? It is a packet of waves, and these waves are an oscillating electric field and an oscillating magnetic field. Now, in a previous chapter, we learned that whenever a charged particle enters an electric field, it will experience an electric force. Consequently, that charged particle will start to experience an acceleration. So, when a photon interacts with an atom, you have two sets of charged particles. You've got the electrons and you've got the protons. But the proton is 2,000 times more massive than the electron. In addition, a neutron is 2,000 times more massive than an electron. Since the nucleus is composed of protons and neutrons, the nucleus is 2,000 times more massive than the electrons in the electron cloud. Therefore, it is the electrons within the atom that undergo the greatest acceleration, or in other words, oscillation, when a photon interacts with the atom. Okay, getting back to this diagram, I told you that the red line represents like a line of photons that are traveling in one direction with the same speed. Now let's use this analogy. Let's assume that these are military soldiers that are marching. And what they like to do is they like to march in a certain way and keep a certain pattern. So let's say the white section here represents a cement parking lot. And so it's fairly easy to keep a nice even pace when you're marching on the sidewalk. But then they run into this little blue section. Let's say that this is mud. And when they enter the mud, their feet start to stick in the mud. Consequently, this is going to start to slow them down. So right here, we start to see that these soldiers, when they start entering the mud, they start to slow down, while the other soldiers continue to march forward. The net effect of this is that the soldiers' marching pattern undergoes a bending, or in other words, a refraction, as they go from one medium into a different medium. Now, as they're traveling in this second medium of muck, they are going slower, as indicated by the closeness of the lines. Now notice this. As the soldiers begin to emerge from medium 2, the muck, and enter medium 1, the parking lot, their speed begins to increase once again. The soldiers that first enter the muck are the first to leave the muck, and what happens is, once again, you get this refraction, and it turns out that the wavefront here is parallel to the wavefront here. The only thing different is there's a displacement. Now, this is only true if medium 1 on this side and medium 1 on this side are the same medium. Now, let's return back to this red laser beam, and I want to show you this. Right now, you see that the laser beam is in medium 1. It eventually enters the second medium. Let's say that the second medium for a second is water. So the beam goes from the air, hits the water surface, and then it's refracted. I want you to realize that this beam also acts in the reverse direction. It's true that my laser beam is right here, but it could have also been down here in the water, and the laser beam's path would still be the same. But there's going to be one major difference I want you to realize, and it's this. It's how we perceive light. We always perceive light in straight lines. What do I mean? Well, let's pretend there's a fish right at this location. And though a fish doesn't have a laser beam attached to it, the surrounding light that reflects off the fish will act like the laser beam, but in the reverse direction. In other words, coming out of the water, entering the air. But notice this. As the beam of light leaves the fish, travels through the water, it hits the surface here, it is refracted, and it heads towards the laser pin. Assume that the laser is actually your eye. What will happen is, as this laser beam enters your eye, your mind will perceive that beam of light as traveling in a straight line, and consequently, your mind will project it backwards like this. You will get the false impression that the fish is located here, but it's not, so this is a virtual image of the fish. If you were a fisherman with a spear and you always aimed your spear at the virtual image of the fish, you would always miss, because the spear does not refract when it enters the water. So always remember, when light enters a person's eyes, the mind perceives light rays as traveling in straight lines. It does not correct for refraction. Even though we have our 4 parameters for this image here, and those would be the incident angle, the refracted angle, the index of refraction for medium 1 and 2, how would we use Snell's law to calculate the index of refraction for medium 2? Well, here's the setup, and since I'm looking for n sub 2, I'll divide both sides by the sine of theta 2, making sure my calculator is in degree mode, and we come up with this formula. I plug in my numbers, and because the first medium is air, it automatically has a value of 1.00 times the sine of 45 degrees divided by the sine of 27.7 degrees. And we end up with an index of refraction of 1.521, which closely matches this value here. And while we're still looking at this picture, I want to point out another term. It's called optical density, and it's related to the index of refraction in the following manner. The higher the index of refraction, the higher the optical density. What does that actually mean? Well, let's take this as an example. Air has an index of refraction of 1. The second medium has an index of 1.52. The second medium has a higher optical density. When you look at the rays of light, this is what you'll discover. The medium with the highest optical density will have the ray of light that's closest to the normal line. The medium with the lowest optical density will have the ray of light that's furthest from the normal line. Now, let's see what happens when I change the angle of the laser beam. Here I am. I'm now moving my laser beam down. The angle of incidence is increasing. So is the angle of refraction. The angle of refraction will always be less than the angle of incidence whenever the index of refraction of the second medium is greater than the index of refraction of the first medium. Now, and what's going to happen when I get my laser beam right on top of the normal line? In other words, an incident angle of 0 degrees. Keep going, and bingo, there you have it. We now see that if the laser beam is aligned with the normal line, then there is no refraction. Okay, in this short video clip, what I want to do is just to show you what happens when you change the index of refraction of the second medium. As I slowly start to increase the index of refraction, notice that the refracted ray bends closer to the normal line, and if I lower the index of refraction, the normal ray bends away from the normal line. So in summary, as you increase the index of refraction, the ray of light bends closer to the normal line, while its angle approaches 0 degrees. Okay, now we're looking at a new situation. And what's different here is the index of refraction for medium 1 is higher than the index of refraction for medium 2. And I need to point out something right now. Do not assume that the top medium is always medium 1. I could actually take these two layers and flip them. Medium number 1 is always going to be the layer where the light source begins. Now while I have this picture up, let's do a calculation involving Snell's law. Let's assume that you have the incident angle and the indexes of refraction for both mediums. You are asked to calculate the angle of refraction for medium number 2. You can easily calculate it in the following manner. So quickly going over this is what we see. I rearranged this so I could find sine theta 2. But in order to find theta 2, I have to take the inverse of the sine function, which is the arcsine. When I do that, I get this new equation here. I just plug in my values, and remember, your calculator has to be in degree mode. Plugging in the numbers, I get something like this, 45, which actually matches what we have here in our diagram. Now, let's watch what happens as I move this laser beam. Here, I'm moving the laser beam to decrease the angle of incidence. As I do this, the angle of refraction also decreases. As the incident beam approaches the normal line, the refracted beam also approaches the normal line. Now, what I'll do is I'll move the laser beam away from the normal line, and I keep moving it, and then all of a sudden, boom, something special happens. At this critical point, you notice that the incident beam no longer travels into the second medium. Instead, it's reflected into medium 1 again. This is what we call total internal reflection. And there is a formula for calculating the critical angle that's needed for total internal reflection to occur. Note, for total internal reflection to be possible, the index of refraction for medium 1 must be higher than the index of refraction for medium 2. Now let's have some fun and calculate the critical angle for this situation. And here's our calculation. Very simple formula, easy to calculate, but confusing for students to interpret. But before I go into the interpretation, I want to point out this little problem with this program. Notice that our critical angle is 48.6 degrees. Notice in our picture, we have an angle of 49.1 degrees. So is our critical angle calculation incorrect? And the answer is no. The critical angle occurs when the refracted beam travels along the interface between the two mediums. Right now, this picture is showing us that we have actually gone a little bit beyond the critical angle. Here's what I want you to remember from a previous slide in this video. When the incident beam was close to the normal line, the refracted beam was also close to the normal line. Therefore, if the laser beam is close to the normal line, it's pretty much guaranteed it will enter the second medium. It's only when you move the laser beam away from the normal line that you have the possibility of reaching the critical angle, and if you do, and then you go beyond this critical angle, you will have total internal reflection in medium number 1. And this phenomena of total internal reflection is very important in fiber optics. When a laser beam is sent through an optical fiber, the beam keeps reflecting off the surface of medium number 1 all the way down the cable without any great loss in the intensity of the light, or in other words, the intensity of the signal. This is why fiber optics are used to send signals over great distances. So, in summary, when the index of medium 1 is greater than the index of medium 2, total internal reflection can occur. If you know the critical angle, then any incident angle greater than the critical angle will create total internal reflection within medium 1. Now, the incident beam is beyond the critical angle. As I slowly increase the incident angle, you notice that the incident beam is just simply reflected in medium 1. It never enters medium 2. Now, I'll slowly decrease the incident angle, And eventually I decrease it to the point that we reach the critical angle, and then when I start to decrease it more, we no longer have total internal reflection. The incident beam is now able to enter medium 2, and we now have our refracted beam. And of course, this would obey Snell's law.